So thank you very much, Bruno, to joining us. Short introduction. Bruno Sportis is the CEO and president of INRIA, the National Institute in France for Computer Science. But he has been also a former deputy advisor and chief member of staff at various cabinet of ministers, the CEO deputy of Tuan, a medical startup, co-founder of an AI startup. So a good experience for tech transfer, which I believe is one of the main focus of you at INRIA. So we are very happy to have you to tell us about your vision of quantum in INRIA. Please, the screen is yours.
Hello to everybody. It's a pleasure to give this talk in this conference, devoted to quantum computing, organized by BPI France, even if this could be better to be with you, of course. So I am Bruno Sportis, the CEO and chairman of INRIA, the French Research Institute for Computer Science and Applied Mathematics. And one topic of growing interest for my institute is actually quantum computing, with a focus on software and algorithmic issues. And these issues have been set at the core of our strategic priorities for the forthcoming years. I think that most of us know that this is a necessary but risky game to play this game of quantum computing. And I like this sentence written in the report by the US National Science Academy about quantum computing issues. We did not find any fundamental reason that such a system could not be built, provided the current understanding of quantum physics is accurate. So this is clearly a risky game, but we have to play it, as said by Cédric O just before. So what is at stake? The ability to master the incredible power of computing provided by a quantum computer if some teams achieve to build it. And this is, of course, an hardware issue, for sure. But there are also a lot of key issues for software and algorithms to be dealt with. And let me illustrate that with some examples. So the first example of such issues is given by quantum-inspired classical algorithms. A quantum computer, which usually referred to as a large-scale quantum computer, can implement algorithms designed to such a computer. For instance, the so-called Shor algorithm, with key possible applications for cryptography with public keys, or the so-called Grover algorithm with applications for the search problems. So such algorithms have been put on the table, so to speak, have been created, have been theoretically proposed in the 90s, but before being able to implement them and to use them at scale, one needs to solve a lot of hardware issues, for sure. But there are also other issues which are related to our ability to make them understood by the hardware. And this is a programming language issue. Without such a language, the most powerful computer would be perfectly useless. And even without a quantum computer, research in quantum algorithms can be useful and can be used by classical computers. For instance, there is a fundamental issue which is still open, that is to say, are there classical algorithms with a performance similar to quantum algorithms? A good example is given by the recommendation algorithm as the one used by commercial platforms such as Amazon and Netflix. In 2018, a young researcher, Ewin Tong, has proposed in her dissertation thesis, whose title is quite clear, a quantum-inspired classical algorithm for recommendation systems, a classical algorithm, that is to say for classical computers, with a performance similar to the quantum algorithm proposed 2 years before by two researchers, which was exponentially faster than the usual classical algorithm. So that is to say that there was a classical algorithm inspired by a quantum algorithm with a performance similar to this quantum algorithm. So this underlines that research in quantum algorithms is necessary and can result, as usual, in an unexpected impact for today's classical algorithm, even if at the end of the day, the quantum algorithm is not built. So dequantizing quantum algorithm is a crucial field of research. The second example is given by the so-called noisy intermediate scale quantum machine, so the so-called NISQ, and the associated algorithm. So existing quantum computers and those that will be available in the near-term future are prone to errors, that's known. And this class of machine is referred as to the NISQ machines. And developing algorithms for such machines, is of strategic interest. So in a nutshell, the idea behind this is that a non-perfect quantum hardware can be made usable by a perfect software, thanks to the power of mathematics. So briefly speaking. Indeed, the algorithm can help the hardware by reducing the error rate. And this is the challenge of error-correcting algorithms in order to reduce the noise of quantum computing, the error related to the so-called physical qubits. So that's why that is critical to work on NISQ machines. So the plan is to develop this technology step by step, starting for small proof of concept systems. For instance, the roadmap of the Paris Center for Quantum Computing, PCQC, which is a key component of the French ecosystem in quantum computing, especially for software and algorithmic issues, is first to build three logical qubits with the correction of errors. And the interesting point is that by removing the correction features, the resulting hardware can allow to work with NISQ machines with tens of noisy qubits. At INRIA, another example, there are many works devoted to error correction and to the control of noise, to switch from noisy physical qubits to safe logical qubits. Some of these works, for instance, those made by Jean-Pierre Tillich in the COSMIC team, are rooted in theoretical computer science. Other approaches are based on multidisciplinary teams. It's very important to have multidisciplinary teams in this field, with researchers in mathematics, in informatics, in physics, and they are based on concepts such as the so-called cat qubits, referring to the Schrödinger cat, of course, with the work of Maziar Miraimi and collaborators in the Quantic team, a joint team between INRIA, Sorbonne Université, École des Mines, École Normale, and the National Center for Scientific Research. And the goal is to give an alternative to fault-tolerant computation with protected logical qubits instead of paying an expense of a significant overhead in a software. So this is a good example. And this also leads to innovation and to new ventures. For instance, the startup Alice and Bob, founded by Théo Perronin and Raphaël Lescan, is based on such an approach. So this illustrates that in informatics, there is no linear scheme of innovation. A breakthrough innovation can stem out straightforward from theoretical research theory. And that's why people like me, who are driven by innovation at the end of the day, are the best sponsors for free academia research, for theoretical research. Very important in this field, I guess. A third example is given by the need of a full software stack for a quantum computer, similar to that which is required for a classical computer. And it's important to stress that building the quantum computer is just one half of the problem. quantum computer is a completely different kind of computer. It's very hard to program. Everything, that is to say the software stack, needs to be reinvented. But the good news is that we can start, and we have already started that to do so now without the actual quantum computer. So the software ecosystem should, for any computer, should include the programming language, the compilers, used to map algorithms onto the machine, but also simulation and debugging tools, etc., etc., optimization tools. So the software stack. I am first focusing on programming languages that are specifically designed for quantum computing. For instance, at INRIA, young researchers, this means researchers hired in 2020, are working on a higher level programming language for quantum computing called ZX Calculus, which is a graphical language. That is to say, a language that represents quantum programs as little drawings, little diagrams, so to speak, on which human reasoning is much easier as compared to directly manipulating the quantum computers and the qubits, which is quite difficult, as you know. And these young researchers were able to prove that such a graphical language is complete. That is to say that any program can be represented by such a drawing. Some of these works are achieved in the so-called MOCA team, a joint team between INRIA, Université de Lorraine, and the National Center for Scientific Research. Another example is compilation optimization. Compilation optimization for a classical computer tries to minimize memory access, and to speed up operations. For NISQ machines, there are currently some works whose goal is to reduce the number of operations in order to reduce the impact of errors, of noise. In this direction, at INRIA, there are some works made, for instance, by Caroline Collange in the so-called PACAP project, which is a joint project between INRIA, Université de Rennes, and the National Center for Scientific Research, in order to use experimental quantum computers and to apply these optimization techniques to such computers. So building the software ecosystem for quantum computing, that is to say, a large ecosystem of people, of developers, of engineers, of researchers, is really a key issue because we have to master all these skills. I have only given some examples, from programming languages to error correction software, to compilation optimization, etc. We have this expertise in France, especially in the INRIA ecosystem, with our partners in universities, in the National Center for Scientific Research. A fourth example is next to quantum computing, but is a strategic issue from my viewpoint, namely post-quantum cryptography. So what is at stake? To design algorithms that can remain secure even against an adversary who has access to a scalable, fault-tolerant quantum computer. So quantum-safe algorithms. So this is a key issue because companies and governments cannot afford to have their private communications decrypted in the near-term future, or even if that future is 30 years away. So that's why research in post-quantum cryptography should be a key priority. This is one major research field at INRIA and in France also. The NIST, so the National Institutes of Standards and Technology, has launched in 2017 an international competition to select some standards for post-quantum cryptography. INRIA teams and with our partners stand for 17% of the 69 projects which have been accepted by NIST. And after the second round of the competition in early 2019, up to 27% of the projects involved INRIA teams with our partners. And this proves that we have to master a lot of skills, a lot of research topics, because these proposals are based on a large panel of skills ranging from code theory to Euclidean networks, multivariate polynomial systems, elliptic curves. To be honest, I do not master these theories, that's clear, but this is only to underline that we need this diversity in our research projects. And also, a startup company was born in this ecosystem of high-level research, namely CryptoNext, funded in particular by Jean-Charles Faugère. And this is another example of the dynamics of innovation in this field, straightforward from high-level research to a startup company exploring a new possible venture, a new business. I have focused here on post-quantum cryptography, but I would like to briefly point out that there are also some very important work in quantum cryptography and communications, especially with projects involved in the European quantum flagship. This is very important to make researchers from post-quantum crypto and from quantum cryptography meet, because both fields feed each other. I want to end with the last issue, the battle for talents. And from my viewpoint, this is really the mother for all battles in this field and in research in digital science more generally. One need to attract many young researchers, many young engineers in this field. And this is difficult because the quantum computer does not yet really exist. But without these talents, this will not be possible for us, for our country, for France, for Europe to play the game. At INRIA this year, we have increased by more than 30% the number of permanent researchers active in this field, in close partnership with the key French universities, with the National Center for Scientific Research, with CEA. And in order to develop new strategic axes, such as quantum simulation in material sciences, such as quantum machine learning, such as the coupling between quantum computing and high-performance computing, it's of paramount importance to attract new talents. So to conclude and to summarize, 3 key points. First, without software, a computer is totally useless. So do not forget software and algorithms. Second, do not forget that breakthrough innovation results from high-level theoretical research in this field and in many other fields. So we have still to invest massively in high-level research. Third, this is a question of ecosystem, as said by Cédrico just before, an ecosystem with universities, with public research labs, with research departments of large companies, with startups, of course, with smart venture capitalists, with smart LPs as well. So that's why such a day is very important. So thanks to BPI France for having organized that, because this is a good illustration of the existence and of the building of a sparkling ecosystem in this field. And that's why launching a French strategy for quantum computing is also so important for our technological sovereignty. So thanks a lot.
Thank you very much, Bruno, for this wonderful, very high spectrum of the topic. We have some questions in the chat. Olivia has a question. Maybe you ask the first one, but we need to go quickly because we have 4 minutes left. Please.
Yeah, INRIA is famous in the artificial intelligence field with scikit-learn. It's a very popular framework used throughout the world. I mean, it's one of the top 5, I think, in machine learning.
Top 3.
Top 3, okay, even better. So do you think we could do the same in quantum computing software development tools? It's probably an important battle, and probably also to compete with the large American companies in that field.
I totally agree. This is a good reference to scikit-learn. We should be as successful as scikit-learn is or was for building a toolbox for data scientists, for data science, for artificial intelligence. We have to build a similar project devoted to the quantum software stack. That's clear, for sure.
Okay, I ask a question from the chat. It's mentioned that quantum technology for cryptography, which seems to be the second marker of the French plan, as mentioned by Cedric O, is just, as you mentioned, is covering the QKD and post-quantum. However, our question is that there are more applications beyond QKD for quantum cryptography, like quantum internet, blind computing, which also provide new possibility of strengthening security. So can you tell us about the plan that INRIA has to expand in this domain of quantum cryptography?
So I guess that INRIA is only one part of the big cake. So I cannot comment what the national plan will put on the table, of course. But at INRIA, this is what I have said. The key issue is to be able to attract new people, new talents. To date, let's say that we have in our within the institute, that is to say within a portfolio, so to speak, sorry for this word, of more than 200 projects. There are a small number of projects which are active in quantum computing or in post-quantum cryptography, but they are of high level, as I have illustrated that. The key issue is to reinforce them, is to attract new people, new talents with our partners, and that's all. And there is the general framework of the national plan. There is the general framework of the strategic plan of INRIA. There are some sparkling ecosystems, for instance, at Grenoble, at Saclay, at Paris, with the Paris Center for Quantum Computing. And that's all. The mother of all the battles is people and talent.
Thank you so much.
Are we able to interest young French researchers, young French engineers to invest in this field, which is a risky game? That's the truth. Are we able to attract European researchers and engineers? Are we able to attract people coming from all countries under the constraint that they are very good to help us to build our ecosystem? That's all.
So it's not just French researchers, it's researchers in France.
Okay, thank you very much, Bruno, for this fantastic coverage of the activity at INRIA and in France. There is plenty more questions, but we have to move on. So over to you, Olivier, for our next speaker. Thank you.